This is question number 16 from TIFR GS 2025 Maths PhD exam. This PhD exam. Question is, let n is greater than or equal to 2 and A be an n-tocent real symmetric and positive definite matrix satisfying trace of A is same as determinant of A. Choose the correct statement that holds for every such A. So we have given us real symmetric matrix which is positive definite. A is real symmetric plus positive definite. So we can check these options by choosing such A which satisfy this condition. Trace A is same as determinant of A, and we can discard the option and we can get the correct option. Also, we can go formally by using the properties of positive definite matrix. So, what is a positive definite matrix? It is a real symmetric matrix which satisfies the condition X transpose A X is greater than 0. Here A is a symmetric matrix, real symmetric matrix. So, I will do this problem by taking a counter example and also by using properties of positive definite matrix. So it has some properties. I am writing here those. You should remember these properties. First of all its eigenvalues are positive, strictly positive, are greater than 0. Next is all its principal minor and leading principal minors are also greater than 0. So by using these two conditions we can find the answer of this question. Let's say I have a matrix of order. I have given that I can choose n is equals to 2 or any bigger n. So let's say I am not considering any n. So A is a n cross n matrix. So it's let lambda 1, lambda 2, lambda 3 up to lambda n are the eigenvalues of A. It implies that since A is real symmetric and A is positive definite, means lambda 1, lambda 2 and all lambda i's are strictly greater than 0. Okay. So what we can do is we can apply here AMGM inequality. So let's see first in the option what they're asking about. It is given that trace of A, determinant of A. So first we will see what is the trace of A and what is the determinant of A. So we have eigenvalues of A, and since A is positive definite, it means all eigenvalues of A is strictly greater than 0. Then determinant of A is nothing but the product of all eigenvalues. Let's say lambda 1 into lambda 2 up to lambda n, or we can write it as product of lambda I is from 1 to n. Let's say I am denoting this product as P. for the simplicity of notation. And what is trace of A? Trace of A is nothing but sum of all eigenvalues lambda 1 plus lambda 2 up to lambda n. Let's say I am denoting, I can write it simpler notation. So lambda I is from 1 to n, and I am denoting it as S. Okay, so this is my sum of eigenvalue and this is my product of eigenvalue. So I am now going to apply the AMGM inequality. Applying AMGM inequality. So let me define here what is AMGM inequality. If x1, x2, xn are greater than 0, xi belongs to R, then x1 plus x2 up to xn divided by n will be greater than or equal to x1 into x2 up to xn raised to the power 1 by n. So I am going to apply this inequality in here. So I have this, I will put here, in the place of sum, I will put my sum of eigenvalues, and here I will put my product of eigenvalues. So I can write here lambda 1 plus lambda 2 up to lambda n is equals to lambda 1, it is greater than or equal to lambda 1 into lambda 2 up to lambda n raised to the power 1 by n. This is my AMGM inequality. So I have denoted this sum as S. So I am writing it as S by n, which is greater than or equal to, this is product, I have written this as P. So it is P raised to the power n. Okay. So now what we can do is, this is my trace. S is my trace and this is my determinant. Okay, so I can do power both side, nth power. I can take nth power. So n raised to the power n, s raised to the power n raised to the power n, which is greater than or equal to p. We will take 1 by n into power n. So it is p. So what we can see from here is sum is greater than product. Okay, sum is greater than product power n. So I can replace this s raised to the power by n, since sum is greater than, product is greater than sum. Okay, if I multiply two positive number and add two positive numbers, since they are uh, strictly greater than 0, so these are positive numbers. So if we product positive numbers and we add positive numbers, then product will always be greater than or equal to sum. Okay, so if this is s raised to the power n by n raised to the power n is greater than p, then we can replace this, because s is also greater than p, p is also greater than n. So n p raised to the power n by n raised to the power n will also be greater than p. So from here what we can write is p raised to the power n minus 1 is greater than n raised to the power n. Okay, now I am going to do 1 by n minus 1th power of both sides. So what we get is p raised to the power n minus 1 by n minus 1 greater than n raised to the power n by n minus 1. From here what we get, p raised to the power 1, we will cancel it out, and this is n raised to the power n by n minus 1. What is this? This is trace of a. Here we have here we have assumed that my determinant of a is p. So it is determinant of a is greater than or equal to n raised to the power n by n minus 1. Okay. Now looking to the options, I have option C, same as determinant of a is greater than or equal to n raised to the power n by n minus 1. So here I have find this I got this option. So by AMGM inequality I got this. How we can show that these options are incorrect? So let's assume I will show it by a counter example. I have mentioned some properties of positive definite matrix here, that all eigenvalues are strictly greater than 0. I have used this property. Now by using this property I can find a counter example for those options, like all its principal minors and leading principal minors are greater than 0. I am going to take a matrix. I am going to choose a matrix which satisfy this condition. Trace of A is equals to determinant of A, and another condition is all the principal minors and leading principal minors are greater than 0, and A is symmetric given. Okay, A is symmetric. So I am going to take a example which satisfy all these three conditions. By that example I will check whether these options are correct or incorrect. So first of all, what is principal minor and leading principal minor? I will explain it now. Let's say my n is 3. I can choose n is 3 because n is given as n is greater than 2 or equal to 2. So I can choose any number which is greater than 2. So this is n, for n is equals to 3. Let's say my A is a symmetric matrix, A11, A12, A13, A31, A3, sorry, A21, A22, A23, A31, A32, A33. Okay, this is my A, and A is symmetric. I have not written this matrix as a symmetric matrix, but I am assuming that my A is symmetric, and so how we will check that all its principal minors and leading principal minors are positive? So principal minors, this is 3 cross 3, and principal minor of order order 1 of A are all the diagonal entries. So A11, A22, A33. So I have said that all the principal minors and leading principal minors should be strictly positive. So it should be positive, it should be positive, it should be positive. This is of order 1, means 1 cross 1. I then again we will choose of order 2 of A are all the principal minors of order 2 of A are, it is determinant of A 1 2, determinant of A 1 3, and determinant of 2 and 3. So if you're confused with this notation, let me tell you what is this. Determinant of A12 means determinant of A, where we are choosing first row first column and second row second column. It is a 2 cross 2 matrix of first row first column and second row second column. Similarly here also first row first column and third row third column, and here also or we can more simplify it like determinant of A12 is A11 first row first column, A12 A21 A22. This is 2 cross 2 matrix. Oh sorry, this. Similarly for determinant of this and this, all should be greater than 0. This should be strictly greater than 0 for a positive definite matrix. And next we will check principal minors of order 3 of A, that is nothing but determinant of A. So we have 3 cross 3 order, so it is only determinant of A here in the case of order 3 matrix. So what is leading principal minor? So leading principal minors are this, for order 1 is 1 1 A11, for order 2 is this is the leading principal minor of order 2, determinant of A first row first column and second row second column. And leading principal minor for order 3 is nothing but determinant of A. So it should be greater than 0. So and we will choose A which satisfy all these conditions. For that A we will check all these options. Okay, so let's say I am choosing a diagonal matrix. Why diagonal? Because diagonal are easiest matrix to analysis anything. Let's say 1 0 0 0 2 0 0 0 3. Okay, so first check whether this matrix satisfies all the necessary conditions, all the restrictions given in the question. So first of all, my A is a symmetric matrix. Yes, it is symmetric. Second, is it a positive definite? Yes, it's all principal minors of order 1, that is 1, 2 and 3. All are strictly greater than 0. Of order 2, principal minor of order 2 is this. First determinant of this matrix will be 2 minus 0, it is greater than 0. And this is 6 minus 0, this is A, determinant of A 2 3, this is also greater than 0. And this one, so 3 minus 0. All two order principal minors are greater than 0 in this matrix. And also principal minor of order 3 of A is nothing but determinant of A. So what is the determinant of A? Here determinant of A is nothing but 6. 1 into 2 into 3, product of all diagonal entries. So it is 3 which is greater than 0, means all the principal minors, leading principal minors are positive and all its eigenvalues are positive. So it is a symmetric matrix plus positive definite. Positive definite. And the third condition, whether it is satisfying trace of A is equal to determinant of A. Yes, determinant is 6, and what is trace? 1 plus 2 plus 3, which is also 6. So yes, it is, this matrix is satisfying my all the necessary criteria. So I can check by this matrix whether my option 1 is true or not. Option A is saying that trace of A is less than n raised to the power n minus 1. So trace is 6, and which is less than n raised to the power n by n minus 1. Here I have chosen 3 cross 3 matrix. My n is 3, so it is 3 raised to the power 3 by 3 minus 1 means what? 3 raised to the power 3 by 2 means 3 raised to the power 1.5, it is 3 root 3. Okay, what is the value of 3 root 3? 3 into 1.7 something. Maybe it is 7.4 or 5 points less than 6. So it is saying that this value 3 root 3 is greater than 6. So it is completely false. This value is, so my option A is incorrect by this example. As, similarly, we will check for trace A is less than or equal to n. No, here I have trace a is 6 and n is 3, and 6 less than 3, it is false. So my option B is also false. All the eigenvalues of A are less than 1 by 2. It is saying that all eigenvalues are less than 1 by 2. No, I have in this option I have eigenvalues 1 2 3 which is greater than 1 by 2 clearly. So this option is also false. So the correct option is this only. And by this example we can check that determinant of A is greater than equal to n raised to the power n by n minus 1. So here determinant is 6 which is greater than 3 raised to the power 3 by n minus 1, means 3 minus 1, which is true. Yes, 6 is greater than 3 root 3. So this my C option is correct. Okay, so that's it. I am showing the whole solution.